So this topic is on partial fraction decomposition, and it's a little bit more complex. There's a few more parts to it, so please make sure you supplement by visiting YouTube and watching other videos, searching the internet. There are a lot of great written step-by-step examples available to you. I'm going to show you a few examples here, and your notes are also provided for you. But I just kind of want to show you what this looks like. So in partial fraction decomposition, the overall idea is that an expression, like you see on the screen, was probably created by adding two fractional expressions together, right? We've been working on adding and subtracting these fractions that have x's in them and things. But we need to figure out which two fractions were added to create this. So that's what partial fraction decomposition does for us. It lets us decompose or break apart something that's larger. The first step would be to factor the denominator. So if I'm going to factor the denominator on this one, that means the numerator gets to stay the same. And it looks like the denominator would break into something that looks like this. Okay? This is our first clue, because you got to remember, if I've added two fractions, at some point in time, those fractions got a common denominator. So looking at that denominator, it looks like I could have added two separate fractions. One probably had an x on the bottom, and one probably had an x plus 1. And then when I multiply them together to get a common denominator, I end up with what's on the left. The tricky part is I don't know what the numerators are. So I'm just going to put an a and a b up there to represent two unknown numerators. Okay? So looking at the a-b fractions, if we were going to add these, we would have to find a common denominator, right? So, which means the a fraction would be multiplied top and bottom by an x plus 1. So really, I was going to have a x plus 1 over x times x plus 1, right? That would have gotten me the common denominator and would have adjusted the numerator. Same with the b, right? I would have had to multiply top and bottom by x in order to get the common denominator and make sure that the numerator is balanced. Now, we've done addition and subtraction with equations before, with fractions, and when we know we have common denominators, right, I would add these two together, the denominator would remain the same, and we've created a new numerator once we combine like terms. We also know that once we have all the same denominators, we can kind of pretend like they're not there, right? They're always going to stay the same anyway. The only thing that's going to be making adjustments at this point are the numerators. So let's examine this and just not pay any attention to the denominator. Let's just examine the numerators as they are. I'm going to distribute that a and distribute the b, so I get something that looks like this. Okay, so on the right, I want to do a little bit of combining like terms, okay? So on the right, I notice that there's two terms that have an x in it. So I could recombine and greatest common factor to create this, right? I have ax plus bx. So if I put those next to each other, I could factor out the x and say a plus b times, so if I recombine them. And then there's all little a there, all by his lonesome. And on the left, we still have 3x plus 2. Okay. So I'm going to scoot this down just so we can look at it. I will scoot it back up in a little bit. So this is what we're working with. This is where we can kind of compare the left to the right. Notice, my x term has a value of 3, which means this stuff must be equivalent to 3. So a plus b must equal 3 because that's how I get 3x. Similarly, I have a that does not have a coefficient, or a variable, I'm sorry, and neither does the 2. So in this case, a must be equivalent to 2. Well, I can recycle that back into the a plus b. So that's 2 plus b equals 3. So the missing b must have been a 1. So a was a 2 and b was a 1. So let's revisit the first equation we started with. Okay? So up here, a and b are no longer unknown, correct? We know that a was a 1 and b was a 2. Or I'm sorry, a was a 2 and b was a 1. So those are the two fractions that got added together to create the 3x plus 2. And you can go ahead and do the math. At this point, you could do combine like terms, common denominators, do the basic process. You will end up where we started. Let's try another one. This will have a slightly different setup because when we factor, it ends up looking different. But we always start the same. Go ahead and factor the denominator. So the numerator remains the same. Okay. Now, it's going to start by looking the same. Something had an x, and something had x squared plus 4. Now, we have an x squared plus 4, which means we need to have 3 variables to represent all the possible x combinations. So the way we set that up is ax, right? And we're going to have a b and a c. So bx plus c is the way we'd set this up. And that's primarily because this term has a squared in it. So we have to get an extra x in the top, right? Where in the previous example, this portion had an x without an exponent, and so it could be represented by one letter. But because this technically is 2 separate factors in the denominator, technically we could break this up. We want to make sure that we have made space and reserved that. All right, so having that done, let me get rid of this arrow here. Okay, we're going to kind of attack this in the same manner. Again, I'm going to ignore the denominators because in the end they go away anyway. So we have 3x plus 2. And then on the right, we're going to have an a times x squared plus 4. And we're going to have bx plus c times x, right? Because that's the term it was missing over there. All right, so this would have gotten us common denominators. Now we're going to go ahead and distribute on the right to be able to combine everything. So we're going to have ax squared plus 4a. And we're going to end up with bx squared plus cx. Now I want to recombine this in standard form the best I can. So x squareds are going to go first. I have 2 of them. So I'm going to greatest common factor out an x squared. And I have a plus b, right? A and b. Then I want to look for anything with an x in it. So the c term has an x in it, right? And then that 4a does not have an x at all, so that's going to go at the end. We're going to compare that to 3x plus 2. So let's figure out what we can figure out right now. We notice that the 4a has no x. Neither does the 2. So that must mean that 4a is equal to 2, because the no x term will belong to or go with the no x term. So a must be 1/2. All right. Next, the c term has an x, so does that. So that must mean that cx, oops, I'm sorry, I should not have put that x in there. Let me back up, sorry. C is equal to 3, right? 3x, cx. So c is equal to 3. The last one is this right here. Notice I have 0 x squareds over here, right? I have none of them. So all that means is that a plus b must equal a 0. Well, we know that a is 1/2 plus b equals 0. So b must be equivalent to a negative 1/2. We can then use these numbers to go back up to the very beginning and put them in their proper places up here. Okay, so I'm going to go through and erase these right here. We know that a was 1/2. Don't worry about cleaning this up just yet. Just write the pieces where they go. Okay. B was a negative 1/2. And then there was an x associated with that. And c was a positive 3. Okay. For right now, I would accept this answer, even though it's a little sloppy with the fractions and a fraction thing, right? I'm just checking to know if you know how to do partial fraction decomposition. Okay? I'm not going to be super picky about getting this cleaned up at this point in time. However, for curious minds who want to know how to clean this up, I'm going to clean it up. But just know that I am not going to require this cleanup as of yet. Okay? So people who want to know how to clean this up, I'm going to do that real quick. I'm also going to make some space here so I can do that. So I'm going to erase some of this stuff so I can clean this up. So if you need it, you can rewind the video and do that. So the first term, 1/2 over x, okay? When you have something like this 2 can technically go down into the bottom. So I'm going to have 1 over 2x going on here, okay? That's what it means. It's 1/2. It's basically you have 1/2, okay, times 1 over x is what you have going on, right? So you have 1 over 2x. Now the second one's a little complicated because I have these pluses in it. Okay, I have these pluses in it, so it kind of messes me up a little bit. However, if I take the numerator of that second equation and I take a greatest common factor out of that, okay, I'm going to factor out a negative 1/2. Right? I'm going to factor out a negative 1/2, which is going to leave me a positive x and a negative 6, right? Because I'm taking out, I'm dividing by half, right? Half divided by half is 1. 3 divided by half is 6. Remember, when you divide by a fraction, your number gets larger. I'm going to use this piece to fix my second term. So my second term would end up looking something like this, right? Instead of the plus in the term, it would be minus x minus 6 in the numerator and a 2x squared plus 4 in the denominator, like that. Okay? So if I were to recombine the whole thing, this part would come over and meet it. So I had 1 over 2x minus this. So this would be the cleaned up fraction. Again, you don't have to do that right now, but just know that that's what it would look like. Okay, I'm going to do one more example, again, because the structure ends up being a little different. So in this example, we notice we have a tripled quantity on the bottom, right? We have x minus 2 to the third power. So these are a little different because if we're adding and subtracting, it means that somewhere along the line, x minus 2 to the third power became the common denominator, but we didn't have any other terms to muddy the waters or add more stuff to it, which means all 3 terms that we used, because we're going to have x to the cubed, right? So we have to have 3 terms, would have some sort of combination of this. So the way we set this up is, again, the numerators aren't going to change. I should go to blue, I guess. The numerators aren't, we're not going to bother with those, but we got to remember that if we had this term for one of our items, we need to create 3 terms that have nothing but an x minus 2 involved. So if I were to add these 3 pieces, 3 because I have an x to the third as my greatest degree, right? So I have 3 pieces, knowing that the largest one became my common denominator. Hence, I need to have 1 representing each progressive step up to x cubed. And we give each one a representative numerator. Okay, I know this one's the tricky one that fumbles people up a little bit. But like the other one, like if one of these denominators was different, I would have a different variable or an x outside or something on that first thing. But since all 3 had something to do with each other, I would set it up like this. After this, everything works out the same, right? If we were to add these and find common denominators, you go one by one and figure out what you're missing. So in the first one, the left side's completely put together. He wasn't missing anything. The a term had an x minus 2 already, so it's missing 2 more of them, right? It had 1, it needs 3, so I give it 2 more. The b term had 2 of them, so it was just missing 1 of the terms. And the c was not missing anything, so we do not have to multiply it by anything to get it to the third power. So like anything else, we're going to expand this and combine like terms. Okay? So the a gets a little bit different because I have to square that quantity. And when I square that quantity, remember when you square the quantity, you square the first, you square the second, and in the middle, you double, and oops, I say double and then I wrote it because I thought double. So hang on. You double, so you square the second, and you double like that. Okay? So if we were to combine, it'd be ax squared minus 4ax plus 4a. And then the b term would be bx minus 2b plus c. Remember, that's all equal to that. All right. So again, I'm going to go through and combine like terms as I can. All right. So I'm going to combine like terms. So I have ax squared. That's the only x squared I have. And it looks like for x terms, I'm going to have a negative 4a and a positive b. And for constant terms, it looks like I have 4a minus 2b plus c. All right. So let's start comparing that to what's on the other side. Well, it looks like this is going to equal a 0, right? So automatically A must equal 0 because I don't have an x squared on the left-hand side. Therefore, 0 times that is 0. The x term, okay? I know that I have 1x over here, which means this stuff must be equal to 1. So minus 4, and I know a is a 0, plus b, altogether I know that should equal 1, because I have 1x on the left. Well, that's 0 plus b equals 1, so b must be a 1. The last one here will be equivalent to a negative 1, right? So for a is a 0, b is a 1, I don't know c, but I know that whole thing equals negative 1. Okay? So I have negative 2 here. So it looks like c must also be a positive 1. So if a is 0, b is 1, c is 1, I can go back up and figure out what 3 fractions I started with. So this was a 0, so that's going to cancel out altogether. I don't have that term at all, technically. And these both were positive 1s. And so if I did the regular addition and I added those 2 remaining fractions together, I would end up where we started from. So go ahead and watch other YouTube videos. There's lots and lots and lots of examples of this topic out there. There's a lot of written examples. If you Google it, and it'll come up with some options. There's lots and lots and lots of options. And you can always ask me questions as well.